Hello students, we will begin with the topic torque acting on a current carrying loop placed in an external magnetic field. In the last lecture we have studied about force acting on a current carrying wire placed in an external magnetic field. In this session we will be studying about torque acting on a current carrying loop placed in an external magnetic field. Consider magnetic field B bar created by any source. We have placed a loop PQRS, also called as coil, in this external magnetic field. This coil may have one turn or many number of turns. This coil at QR and PS is making an angle of alpha with the external magnetic field, and at PQ and RS it is making an angle of 90 with the external magnetic field. That is, it is perpendicular to the external magnetic field. This is the top view of the same diagram. As you see, this QR is making an angle of alpha with the external magnetic field. Current I is flowing through this loop in clockwise direction. As this current carrying loop is placed in an external magnetic field, it will experience force. We will be finding two things, force and torque acting on this loop, because we know that there are two motions, that is linear motion and rotational motion. For linear motion, we have to consider force, and for rotational motion, we have to consider torque. First, let us calculate force. We will first calculate the force acting on PQ part of the wire and denote it by FPQ. Direction of this force on PQ is given by right hand rule. According to this rule, align the pointing finger of right hand in the direction of current flowing through PQ, middle finger in the direction of external magnetic field, then the thumb will point in the direction of force experienced by PQ part of the coil. Over here it will be inwards. In the last session we have derived a formula for force acting on a conductor placed in an external magnetic field. It is given as force is equal to ILB sin theta, where I is the current flowing through the conductor, L is the length of the conductor, and B is the external field in which the conductor is placed, and theta is angle between the length of the conductor and external magnetic field. The same formula we will be using to find force on PQ part of the coil. So FPQ is equal to ILB sin theta, where I is the current flowing through PQ, L is the length PQ, and B is the external magnetic field in which the conductor PQ is placed, and theta is angle between length PQ and the external magnetic field. We see that the direction between the angle between PQ and external magnetic field is 90. So instead of theta we have substituted 90 over here. We know that sin 90 is equal to 1. So FPQ will be equal to ILP. And the direction of force on PQ is inward, given by right hand rule. Next, we will find force on QR. The direction of force on QR is given by right hand rule. According to this rule, align the pointing finger of right hand in the direction of current flowing through QR part of the coil, middle finger in the direction of external magnetic field, then the thumb will point in the direction of the force experienced by QR part of the wire. Over here it will be in downward direction. Force on QR is given by the formula FQR is equal to I is current flowing through QR, W is the length of QR part of the coil, B is the external magnetic field in which QR is placed, sin Alpha. Alpha is angle between W and B. If you see over here, angle between W and B is alpha. And the direction of this force, FQR, is downwards, given by right hand rule. Similarly, let us find force on RS part of the coil. The direction of this force on RS is given by right hand rule. Using the same right hand rule, we can obtain the direction of force acting on RS as outward direction. And the formula for force on RS is given as ILB sin 90, where I is the current flowing through RS, L is the length of RS part of the coil, B is the external magnetic field in which RS is placed, and theta is equal to 90 as angle between length RS and external magnetic field is 90. We know that sin 90 is equal to 1. So FRS will be equal to ILB and it is in outward direction given by right hand rule. Also let us find force on SP part of the coil. The direction of force on SP part of the coil will also be given by right hand rule. If we make use of right hand rule, the direction of the force on SP will be in upward direction. And the formula for force on SP is given as FSP is equal to IWB sin alpha, where I is the current flowing through SP part of the coil, W is the length of SP part of the coil, B is the external magnetic field in which SP part of the coil is placed, and alpha is angle between SP and external magnetic field. These are the four forces acting on the four straight conductors forming the coil. Also, these four conductors are bound to each other, so they can apply force on each other and they cannot be separated. We see that force on PQ and force on RS is equal and opposite in direction to each other. One is in inward direction, other is in outward direction. Also, force on QR and force on SP is equal and opposite to each other. That is, one is downward and other is upward. So all these forces will cancel out each other and this coil will have no linear motion. But what about torque? Will this coil experience torque? Torque is couple of forces which causes rotational motion. Torque is caused by couple of forces. Couple of forces means two forces which are equal and opposite and act along different points on the same body. Over here, forces on QR and SP are equal and opposite, but they act along the same point on the coil. So they will not form couple and there will be no torque action on these two parts of the coil. But forces acting on PQ and RS are equal and opposite and they are acting along different points on the same body. So the forces on PQ and RS will create a couple, so it will cause torque and this coil will start rotating in anti-clockwise direction. So we have seen that couple of forces on PQ and RS will cause torque and hence the coil will start rotating in anti-clockwise direction. Let us find the amount of torque the coil will experience due to couple of forces on PQ and RS. The formula for torque is equal to force on one of the conductor multiplied by perpendicular distance between the two forces. This is the direction of force on PQ and this is the direction of force on RS. The force on these conductors is IBL. We have derived this already. And the perpendicular distance between these two forces is QC. Over here, QR is the conductor with length W, and QC is the perpendicular distance between the two forces on PQ and RS, which causes torque. So torque is equal to force acting on either of these two conductors. So force acting on PQ is ILB multiplied by perpendicular distance between the two forces. Perpendicular distance between the two forces is QC. Let us draw area vector of this coil. Area vector of an object is always perpendicular to the object. This is the QR part of the coil. So this will be the direction of area vector denoted by A bar. Let angle between area vector A bar and QC be denoted by theta. From the diagram we see that angle alpha plus angle theta is equal to 90 degree. So angle theta will be equal to 90 minus alpha. Now consider triangle QRC. We know that sum of all the angles of the triangle is equal to 180 degree. Over here angle C is equal to 90 degree. So sum of the remaining angles of the triangle will be equal to 90 degree. This angle is alpha. So this remaining angle of the triangle, that is R, will be equal to 90 minus alpha. But we know that 90 minus alpha is equal to theta. So angle R will be equal to theta. In this right angle triangle QRC, QR is hypotenuse. QC is the side opposite to angle theta. So QC will be equal to QR sine theta. The measure of QR is W. So instead of QR, we will substitute it as W, and QC will be equal to W sine theta. So in the formula for torque, let us substitute instead of QC, W sine theta. Length multiplied by width of the coil will give us area of the coil. So instead of LW, let us write it as A, meaning area of the coil. For n number of turns of the coil, torque will be equal to number of turns of the coil multiplied by I, A, B sine theta. This is the formula for torque acting on a coil placed in an external magnetic field, where N is the number of turns of the coil, I is the current flowing through the coil, A is the area of the coil, and B is the magnetic field in which the coil is placed. Theta is the angle between area vector A bar and external magnetic field. So in today's session, we have studied about torque acting on a current carrying loop placed in an external magnetic field. Thank you, students.